Aerospace companies are currently proposing multi-megawatt to gigawatt scale GPU compute infrastructure for orbit. But placing terrestrial server racks in a vacuum creates an immediate problem. There are zero convective air currents to carry heat away from the electronics. Delivering gigawatts of solar power in space is a solved engineering challenge. The actual bottleneck is the inverse. Every watt of electrical power consumed by a processor eventually becomes a watt of waste heat, and in a vacuum, rejecting that heat is the primary constraint. This is the Stefan-Boltzmann law governing vacuum heat rejection. It dictates how much heat a surface radiates into the void. The critical variable is temperature. Radiative flux scales to the fourth power. Small increases in temperature result in exponential gains in dumping heat. Modern AI accelerators generate low-grade heat, requiring cold plates that operate between 330 and 370 Kelvin to stay within silicon reliability limits. Relying on these conventional coolant loops in space creates a massive footprint. At 330 Kelvin, the structural radiator area required to reject that heat quickly challenges the capacity of heavy-lift launch vehicles. To reach gigawatt-scale compute, the architecture must be dictated exclusively by thermal physics, rather than terrestrial server standards. Because of the fourth power law, raising the rejection temperature is the most effective physical lever for reducing radiator mass. This data breaks down ideal radiator area per megawatt. Rejecting 1 megawatt at a terrestrial coolant temperature of 330 Kelvin requires over 1,600 square meters of ideal radiator area. Push that rejection temperature to 600 Kelvin, and the requirement drops to 151 square meters. A 600 Kelvin radiator needs only 11% of the surface area required at 330 Kelvin. The incentive to operate hotter is a massive reduction in structural mass. One proposed solution is to use a thermodynamic heat pump, using a compressor to lift the 330 Kelvin GPU waste heat up to 600 Kelvin before radiating it. This maps a Carnot cycle heat pump attempting that temperature lift. Forcing low-grade heat across such a large delta requires a massive work input to drive the compressor. This electrical work converts into additional heat that the system must also reject. This added load can negate the area reduction gained from the higher temperature. At 50% of the ideal Carnot efficiency, lifting 330 Kelvin to 600 Kelvin requires compressor work equal to 164% of the original IT heat. This effectively doubles the total electrical power generation required by the facility just to run the cooling system. Heat pumps create significant power and complexity penalties. The more scalable path involves developing high-temperature compute hardware and titanium water heat pipes that operate directly in the 450 to 600 Kelvin range. Early multi-rack pilots in low Earth orbit are often constrained by launch volume. This creates pressure to pack hardware as densely as possible. However, packing radiators into dense parallel farms, or fin packs, overlooks a crucial fact. In a vacuum, total material area is not the same as radiating aperture. This is due to the view factor. If you pack hot radiator surfaces tightly together, you create a radiative cavity. Instead of emitting heat into space, the surfaces simply exchange thermal energy with one another. This chart visualizes Monte Carlo view factor estimates for parallel panels. If you separate two hot square panels by a distance equal to 10% of their width, the mutual view factor reaches 0.83. In this configuration, 83% of the radiation emitted from one face is absorbed by the neighboring panel. The critical requirement is optical escape aperture. A radiator is only effective when the photons it emits have unobstructed angular access to a cold sink. Achieving high escape efficiency requires geometries that open up, using widely spaced flat planes or expansive radial fans that point directly into the void. Space radiator performance depends on escaping photons, not just total surface area. Dense, three-dimensional geometries fail because they block their own escape paths. Scaling up to a megawatt-class facility in Earth orbit changes the thermal environment. The sky is no longer a perfectly cold sink. Radiators in Earth orbit face continuous thermal contamination, absorbing Earth's infrared radiation, reflected planetary albedo, and direct solar incidence. While coatings in photonics can mitigate these environmental loads, they are incremental optimizations. They help manage the heat balance, but they do not eliminate the black body limit. You can use angular selective emitters to block radiation from the direction of Earth, but this often requires sacrificing useful cold sky emission angles in other directions. This bar chart shows the impact on a 330 Kelvin radiator using an optical solar reflector coating. Even with this protection, the panel absorbs 170 watts per square meter of solar load at Earth's distance, consuming 28% of its total emission capacity. Over time, atomic oxygen and ultraviolet exposure degrade these coatings, further increasing solar absorption and reducing the system's margin. These environmental constraints are visible in the International Space Station's thermal loops. They require a massive physical footprint just to manage the relatively modest heat loads of a crude laboratory in orbit. The thermal contamination of Earth orbit creates a significant mass penalty for low-temperature radiators. For gigawatt-class systems, moving into deep space provides a cleaner thermal environment, where sunshields can offer near-total isolation. A gigawatt-class facility is most thermally efficient in Sun-Earth Lagrange Point 2, or a heliocentric orbit. But at this scale, tens of thousands of square meters of radiator panels guarantee continuous strikes from micrometeoroids and orbital debris. Liquid droplet radiators are often proposed to reduce mass, but they introduce severe operational hazards. Even small amounts of fluid loss or optical contamination of solar arrays make them difficult to manage in a continuous compute environment. Instead, the architecture must function like an industrial plant. A gigawatt facility requires highly segmented liquid loops and replaceable thermal cartridges, allowing the system to isolate a puncture in one segment without losing the entire facility. However, solving the thermal geometry by moving to deep space introduces a final constraint: light-speed communication latency. Distances at L2 or in heliocentric orbits introduce delays measured in seconds or minutes. This removes the possibility of interactive cloud compute or real-time data backhaul to Earth. The network architecture must adapt to these delays. The swarm relies on high-bandwidth local optical meshes for compute operations, using delay-tolerant networking protocols to synchronize with the ground. At this scale, the deep space environment restricts economic viability to high arithmetic intensity, low-output workloads. This includes autonomous science processing or large-scale AI training runs that can be staged over time. The final architecture balances high-temperature levers, optical aperture requirements, and environmental isolation. On the sun-facing side of a heliocentric gigawatt swarm, a massive thermal sunshield is integrated with the solar arrays, providing both power and shade. In the permanent shadow behind that shield, the hardware operates in an artificially cold environment. This is a sparse, distributed network of titanium water heat pipe panels, rejecting feed at 500 Kelvin, while being actively maintained by robotic repair arms. Every element of this design, from its extreme operating temperature to its optical sparsity, is dictated by the physics of escaping thermal photons. Terrestrial data center instincts are a poor fit for this environment. Heat pumps add too much power load. Dense radiator packs trap their own heat, and low Earth orbit is too thermally contaminated for industrial efficiency. Gigawatt-scale AI compute in the solar system demands a departure from terrestrial design. The result is an autonomous, distributed industrial swarm, purposefully isolated in deep space to satisfy the thermodynamic laws of the vacuum.